So let's go back to where we were yesterday. If you have this trend written here, I said I misspoke on Monday. This should be, they're both, so decreasing from left to right and then decreasing from top to bottom for nucleophilicity. So if you have a nucleophile, the trend is as you go from left to right on the periodic table, the nucleophilicity drops or it becomes less nucleophilic. And then as you go from top to bottom, the nucleophilicity decreases. And I think I had increasing. So if you have your notes from Monday, go ahead and edit that and correct it. And the protic solvent trend is the same. It decreases from left to right, and then it increases from top to bottom. And then this is the same trend, whether there's no solvent or if it's aprotic.
Okay, okay, I think I got confused. Can you repeat, what am I fixing?
Okay, give me 1 second. Okay. So right here, when we first started talking about this, and I gave you the trend for nucleophilicity, I said that it decreased from left to right, which was correct, but I said that it increased from top to bottom, which was incorrect. So this needs to be decreasing, not increasing. Yeah, my apologies for that. And then if it's in a protic solvent, this was correct, right? So it decreases from left to right and it increases from top to bottom. So in a protic solvent, the nucleophilicity of a functional group or a particular atom gets better as the atom gets larger, right? I said that over here as the atomic radius increases. So let's look at, take a couple of more of these examples, and then we're going to move on to elimination. So I want to do, we'll do C, and we'll do D, and we'll do F, C, D, and F. So let's do that. So we have, add a page. Right, so we have in C, we got 3 nucleophiles. We got water, no, sorry. We have ethyl sulfide, the ethoxide, and the acetate anion. So it's here. So this is one of my nucleophiles, and then here. This is one of them, and then the other one is here. Right, and it asks us to rank them in order of increase in nucleophilicity. So from worst to best. And this is done, these nucleophiles are in ethanol. I'm sorry, methanol. So the alcohol itself, is that protic or aprotic?
The which one? I'm sorry, I didn't hear you.
The alcohol, the solvent. Because when it says, let me go back to the question. When it says up here in CH3OH, this is the solvent. And that's knowing what the solvent is helps us to answer the question, which one is more a better nucleophile, right? And the trends are for aprotic solvents or protic solvents. So the top trend where we said that it decreases left to right and decreases top to bottom, that's for either no solvent or aprotic solvent. And then what we said, it decreases from left to right, but increases from top to bottom, then that is for a protic solvent. So if we're in a protic solvent, which methanol is, right? What's the trend? It is decreasing, increasing, decreasing from left to right, increasing from top to bottom. So let's take the, which one is going to be the best, right? Keep in mind, sulfur and oxygen, there's no left to right on that because they're in the same group. They're in the same column on the periodic table. So if sulfur is below oxygen, right? So you have oxygen here and then sulfur here in the periodic table. And the trend is that the nucleophilicity increases from top to bottom. Which one of those is going to be a better nucleophile?
Sulfur.
Sulfur. Good. So this is the best of the two. All right. Good. 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 Now, if we look at the other two, we're comparing both of those are oxygen, right? What is it about this nucleophile here that's different from the ethoxide, other than the structure, obviously? But if we have a carboxylate type functional group, what can that do? If it's a, like, this is the same as an allylic anion, which
Is it with the intermediate?
yeah. So if I have something like this, if I have a negatively charged atom that's attached to a pi bond, what can I do with that?
You can break it and
Can I do this?
yeah. Oh, yes, yes,
I
yes.
can
Yeah.
do resonance with this, right? Right. If I can do resonance on my nucleophile, that's going to stabilize it, right? So this nucleophile is stabilized as compared to the ethoxide anion, which is above it, where those electrons are just there and they're able to be donated. So of these two, which one do you think is going to be better? One what that has its electrons tied up in resonance and less able to donate, or one that's able to donate immediately? What do you think?
The one that's able to donate immediately.
Good. So that means that this is, if the sulfur is the best, that means that this is the worst of the two. So we had to rank them. This would be 1, 2, and 3, where 1 is the best and 3 is the worst. So your nucleophile, the fact that the anion down here is stabilized by resonance, anytime you add stability, you're going to decrease reactivity, right? Something that's less stable is going to be more reactive. Something that's more stable, it will be less reactive. So when you see an opportunity like this where resonant, where your nucleophile has the opportunity to do resonance, then that's going to make it less nucleophilic. All right, let's do, what do we say? Let's do D. It's in acetone, so we're going to do that real quick. There's CH3NH2, CH3SH, and CH3OH. And acetone. What type of solvent is acetone? Is it protic or aprotic? That's
Aprotic.
good. That's the key to answering this question. is aprotic. So the trend in aprotic solvents is decreasing from left to right and decreasing from top to bottom. So what we're comparing is oxygen. Let me put some lone pairs in as the nucleophile, sulfur as the nucleophile, and then nitrogen as the nucleophile. So these are the three atoms that we're looking at. In the periodic table, it is nitrogen, oxygen, and then sulfur. All right, so which one is the best? If it decreases from
Nitrogen.
good, excellent. So this is the best. And then which one is the worst?
Sulfur.
Sulfur. So when you're in aprotic solvent, that's the trend, right? No, that's really based on how basic the atom is, in addition to how electronegative it is. So those two factors, the basicity, and this is a very nuanced topic. And there are a lot of different proposals as to why the trend is what it is, but it's loosely based on how electronegative the atom is, but it's also based on how basic the atom would be as the conjugate base, right? So if it's a really highly stabilized conjugate base, then it's going to be less reactive, because everything comes back to how stable the charge is on the particular atom. So it's the same concept or the same idea from part one when we studied pKa. We could look at the acid or the conjugate acid, look at the pKa. If it has a low pKa, then that means that the conjugate base is very stable and is not as nucleophilic. All right. Let's go to here. We're going to start talking about elimination. So I'm going to, we'll go back to the beginning, to the top. All right, and we're going to start here with E2. All right, so E2 elimination is, and I'm going to cut this out and put it on a different page. That way there'll be a separate section on elimination. And I'm going to talk about the E2, just like I talked about the SN2. We're going to talk about the rate law. And it's not going to be as, it's not going to take as much time, simply because the E2 and the SN2 have very similar characteristics. All right, so we're going to take, for E2, we're going to take this example. We're going to use that. All right. So for let's go through like we did before and just look at predicting the products. Right. So for E2 elimination, that's going to require a strong base. Right. You have to have a base in order for this to happen. And the preference is tertiary or secondary carbons. Right. There's a reason for that. The reason for that is the stability of the product actually guides the reaction. So the more stable product is going to be favored. And as far as alkenes are concerned, because that's what we're making, more substituted alkenes are more stable, right? So let me add that in here. A tertiary and secondary carbon will result in a stabilized alkene. Uh-oh. My brain is working faster than my index finger. Right? If you remember from part one, when we studied, I say we, like y'all were in my class. Some of you took the online class over the summer though. What is the result of any elimination reaction? Anytime you do an elimination, what do you get in the product? Anybody? So elimination always results in the formation of a pi bond in the product. It can be a double or a triple bond, but it always results in the formation of a pi bond. Right. So here in this example, and we're going to use the same methodology, that ICE method. Identify, characterize, execute. So we see this is our leaving group. This is our substrate. This is the base. This is my solvent. All right, my solvent is a product. You cannot do E2 elimination in a product solvent because the base will just react with the solvent. So you got to have an a product solvent. All right. What happens in an elimination, and we're going to go through the mechanism. I'm not going to show the arrows here because I want to use the other example to do that. But you have your adjacent to your leaving group, you have an alpha, we call this an alpha carbon, right? And that carbon has hydrogens on it. Is that right? This is a CH3. So there are 3 hydrogens here. We got 3 hydrogens on this carbon. Right? Those hydrogens, we call them alpha hydrogens. All right, and then so what happens in elimination is the base is going to remove one of those alpha protons, and that's how your double bond is formed, because as that proton is coming off, the leaving group is leaving at the same time, so it's all concerted. So every elimination results in the formation of a pi bond. So that'd be that plus NH3 plus Br minus. Now don't worry about it if it's a little foreign, because we're going to go through the mechanism and all that stuff in a second. All right, so you always look for your leaving group and you look for the carbons that are adjacent to the leaving group. So that's what an E2 eliminate. Well, every elimination is going to give you a pi bond in the product, but the E2 elimination has specific requirements. You need a base. It works best on secondary and tertiary carbons. You need a product solvent. And there's another requirement that I'll talk about as we go through this other example. All right, any questions about that?
I thought I had one. I guess not.
If it comes back to you, just interrupt. That's fine.
Okay.
Or it may come back to you when we start doing the other example. So let's do that. Let's take this example right here. I cut the leaving group off, my bad. The leaving group is iodine. It's hard to see up here anyway, so we'll put some electrons around it. All right, and KOH is my base. So this example here of an E2 is going to help us to flesh out like some of the other characteristics. All right, so with the KOH, don't get confused by that. It's K plus and OH minus. Just a salt, right? So it's the OH part that's the base. So the best strategy for thinking about elimination is to find the leaving group. That's the first thing you want to do. And we know at this point that my leaving group is usually my most electronegative atom or functional group, right? So this is my leaving group. The second strategy, second part of the strategy is to find the alpha hydrogens. Where would they be here in this example?
Will they be to the right of iodine?
So
Iodine?
here, hold up, let me get the right highlighter. Here, there is a hydrogen there. Yep, I agree. What about the other side? On that card,
Yes.
there's some hydrogens there too, is that right?
Yeah.
So those are my two sites that are going to eliminate. And with that being said, the elimination is going to happen at both sites, not at the same time, but it's also going to give us two products because you have two sites that can eliminate. So you're going to get two products. And this is a competition. One of the products is going to be favored over the other, right? Anybody remember that phrase that we use when we talk about product formation, and if there's a ratio of products and or a certain percentage of one product and a percentage of the other product? Anybody remember that phrase? The first word was product, but there's a word that came after it.
Are you mean like the minor and major products?
Yes, that's exactly what I'm getting at. But that was a term or a phrase that we use to describe the fact that you get minor and major. It was called the product distribution.
Oh, all right.
No, don't apologize. You're right. I mean, there's going to be a minor product, which is going to be present in a smaller amount. There's going to be a major product, which is present in a higher amount. So you're right. It's just the terminology. I want to make sure we remember that. Product distribution, right? So there's going to be a minor and a major product. All right, so let's go in. What side do you want to do first? You pick.
We can do the single hard, well, the one to the right first.
All right, so let's do that. So the OH minus is here. It's going to come in, donate a pair of electrons there, and do proton transfer. At the same time, I'm breaking the CH bond like that, right? And I'm going to use the electrons in that CH bond to make my pi bond. And I'm going to displace the leaving group all at the same time. This is concerted, right? It's concerted. If I ask you what the rate law was for this reaction, if you know it's concerted and the base and the substrate are both involved in the rate determining step, which is the loss of the leaving group, what would you say the rate law was?
Yeah, I'm a little fuzzy on that one.
No, that's okay.
Is that the formula K times the substrate?
Mm-hmm. So let's think back to the SN2. And I did a poor job of illuminating what that 2 means. That 2 says that the transition state is bimolecular, or the transition state for the rate determining step is bimolecular. Right, that alone means that there's going to be a 2-term rate law. Just like SN2 is nucleophilic substitution, is bimolecular, and then SN1 is unimolecular. E2 is elimination, bimolecular. So that means that there are 2 things involved. So 2 things involved in that rate determining step. That's all that means. It's a fancy word, but that's what it basically means. So what two things do we have coming together here or reacting here? We have the base, is that right? And then we have the substrate. If both of those things are involved in the rate or in determining the rate, what's the rate law? Somebody already said the substrate is the concentration of the substrate matters. What about the base?
Would it be times the base 2?
Yes, because it's bimolecular. If it's just like SN2. SN2 is the substrate and the nucleophile. SN1, which is unimolecular, was just the substrate. Here, it's the substrate and the base. And then you'll see when we do E1, it's just the substrate, just like SN1. So the rate law, the rate is a second order rate law. Right, second order overall, first order in substrate, first order in base. So anything you do to the base is going to affect the rate. Double it, triple it, quadruple it, cut it in half, whatever. It's going to have an effect on the rate. And go ahead. Did somebody, were you asking a question? All right. Anything you do to
Oh, no, I didn't say.
okay. All right, no problem. Anything you do to the substrate is going to affect the rate. Double it, triple it, cut it in half, quadruple it, sextuple it, whatever. It's going to affect the rate. So this is what the proton transfer looks like, and it's all happening at the same time. So the base is coming in and pulling off proton. The electrons from the CH bond are being used to make the pi bond. So we're going to put a pi bond right here. And then I'm losing that iodine all at the same time. So that particular product, I'm going to write it in, I guess I can write it in blue. That particular product is going to look like this. So make sure I don't put too many carbons. Right? Are y'all following that?
Yeah.
That's my product. So that's the first product. The other product is going to happen when another molecule of base attacks this. Should I rewrite it, or are y'all okay me working on the same structure?
I think if you use a different color, it should be fine.
All right. So we're going to have, I'm going to do this in, I'll use green. So the OH can come here and attack the other side now. This is not happening at the same time now. It's, you get one product, but there's Avogadro's number of molecules of this alkyl halide in 1 mole. So you got a bunch of those, you got a bunch of base. So this is happening on different molecules. Now the reactions might be happening simultaneously, but they're not happening on the same molecule. They're happening on different molecules. Right. So this is going to be here, attack there. I'm going to attack. I'm going to use those electrons to do that, and then break the carbon iodine bond. So it's the same process, just on the other side, and I'm gonna have a double bond right here. Anybody not see that? Right, so that product is gonna look like this. Like that. Yes or no?
I agree.
So elimination, anytime you do an elimination, you're gonna get a double bond, right? Every time. And for E2, you need a strong base. So there's a list of bases. It may not be here. It may be, it's in the elimination video, which I apologize for not sending it ahead of time, but I was finishing a grant and I've been working on that thing forever. So, but I'm done now. So I'll put everything together that you need today before I go over to Kresge. All right. So here's the question now. There's two questions. Then we're going to talk about the transition state and all that good stuff, just like we did for SN2. All right, over here, if we look at these two products, we can see that this double bond is what? Tri, substituted, mono, di, tetra. Then we talk
So
about
the blue one,
the blue one. Yes,
is that tri?
it's tri substituted. Good. And then down here, what about that one? The green one,
Di.
di substituted. Well, I think we talked about this. I forget what reaction we were looking at though.
I remember talking about this, but I think it was for like
It was a lily bromination, I think.
yeah.
Yeah. Right. So di substituted and tri substituted. That matters. For a double bond, the more substituents I have on it, the more stable. I know I talked about this. The more stable it's going to be. Right? Because I remember talking about these carbons being sp2. Right? And then these carbon-carbon bonds donating towards that and stabilizing the sp2 carbons. So there's dipoles all the way around this thing. So the more substituents you have, the more stable the product is going to be. So for the tri-substituted product, this is going to be major. And then the di-substituted is minor because this is more stable. Right? You can predict the major amount of products for any elimination using what we call Zaitsel's rule. So all your eliminations are going to follow Zaitsel's rule. And all that says is that the more substituted alkene in the product is the major product. Right. So anytime you have a question about for an elimination, what's major, what's minor, it's always the more substituted alkene. Now we don't have percentages because, I mean, in order to do that, you have to do this in a lab and isolate each product, get the percent yield for each one, so on and so forth. But in a case like this, where you have two alpha sites, you're going to get two products. All right. Any questions? So let me ask this question. Well, what would the transition state look like for that elimination?
So with that, would it have an intermediate since it's concerted, right?
Exactly. That you're exactly right. There's no intermediate. What I'm asking about is let's just do this side, the transition state. So let's say the base is here. If I'm doing proton transfer, and I'm going to erase these bonds right here. So I'm going to put dotted lines in. If I'm doing proton transfer, right, the base is attacking right here. Is that right? Is that bond partially formed or partially broken? If the OH is attacking hydrogen to make a bond with it, is that partially formed or partially broken?
You said it's attacking to make a bond?
Yes.
So it's partially formed?
Yes, good. What about this one? I'm pulling the proton away from this carbon.
It's partially broken.
Partially broken. What about this one, where I'm losing the leaving group?
That's partially broken.
Partially broken. And then here, where I'm making
right
The pi
partially
bond.
broken. Since it's,
While making the
well,
pi bond.
yeah, I think it's partially broken since it's leaving.
The iodine, yes.
Um,
Uh-oh.
the bond is being broken to,
But the pi bond right here, we're making that. So if you're making a bond, that's going to be partially formed. The pi bond. So this is the transition state for E2. So that's partially formed. This is partially formed. Right, the CH bond right here is partially broken. And then the CI bond is also partially broken.
I think my Wi-Fi cut out. If you didn't hear what I was saying.
I didn't. Go ahead.
No, I was just saying, well, I was just saying that the iodide bond is partially broken. That's all.
Yes, that's correct. Right. So this is what the transition state would look like. And this also brings up another point about this reaction, and that is the position of your alpha hydrogen and your leaving group. There is a what we call a geometric constraint on this reaction. I'll say E2. So it follows a geometric constraint. Your alpha hydrogen and your leaving group, in order for this to actually happen properly, they have to be what we call, and I'm gonna go back to the transition state and show you. They have to be what we call anti. What does anti mean?
Against.
Opposite.
Against or opposite.
Against.
Good. That's right. So anti-periplanar. So they have to be on opposite sides of the same plane. That's the peri, same plane. Right. So if you notice in the transition state, the hydrogen is here and the iodine is here. That's the requirement, that they have to be opposite on the opposite side of the same. So if the plane is like, if you took your hand and put it up against the side of your hand and put it up against the screen where the hydrogen was above your hand and the iodine was below your hand, that's what I mean by that. So the plane is there and the hydrogen is above the plane, iodine is below the plane. If we had to think about this in terms of organic one, and we did a Newman projection, your hydrogen would be here. And this is just a random Newman projection. And then your iodine would be here. I'm just going to put R and R. All right, and if notice too, if the hydrogen that's leaving is always on a carbon adjacent to where you leave, well, the hydrogen that's being pulled off, the alpha hydrogen is always next door, because there's also a hydrogen on the carbon where iodine is, but you never touch that one. That has to stay. So again, you see that they're opposite to one another. And if you, just in case you don't remember, this is called a Newman projection. Right, that has to happen. It's really an orbital argument. So certain orbitals have to line up in the transition state in order for electrons to be shared, in order for the electrons that are shared to be shared the way they are. If the orbitals don't line up, then the elimination can't happen. What's the charge overall on the transition state? Let's do the same thing we did for SN2. What would the charge be? If this is negative or partially negative, And then this is partially negative. It's very similar to the SN2, isn't it?
Is it negative or is it?
Overall. Yeah, you're right. The overall charge is negative.
Okay, now, can you explain why it's negative?
Yeah, sure. So when the iodine leaves, right, it's leaving with a pair of electrons. So iodine itself is going to be negative when it leaves. When the OH comes in, let's go back up to here. You see how the OH is negative when it's coming in? So it has a negative charge already. So the iodine leaving and becoming negative and the OH coming in negative means that there's going to, both of those species are going to be partially negative in the transition state when they're making the bonds that they're making or breaking the bonds that are being broken. If that makes sense.
Okay, so if one of those, well, I'm not sure if they were positive, it would work, but if one of those were positive, would it just be neutral?
Yes, the
Or would
overall
it-
charge will be neutral.
Okay,
Yeah, but because they're both negative, then it has an overall negative charge,
okay,
which is why the solvent needs to be polar. I didn't mention that, but that's one of the characteristics too, that the solvent, not just protic, but polar, not just aprotic, but polar aprotic.
and that's specifically for E2, or does it have to be polar for the other ones too?
Well, it helps with the SN2 as well because the nucleophile normally is charged. So a polarized solvent is going to allow for that. It's going to make that, it's going to facilitate that reaction if it's aprotic.
Okay.
All right, we got to stop here. I promise you I will have recordings uploaded today. I'll also have the notes uploaded from Monday and Wednesday. And then I'm going to send you the elimination videos to reinforce what we discussed today. You could also check the syllabus to see the, excuse me, in the substitution and elimination section of the syllabus. You can check that and you can look at the sections and the chapters that are there. That's fine too. Or if you're doing both, that's even better. Using the book, using the videos, using some outside resources, you can't lose. All right, I'm gonna stop here and then I'll see y'all